Hello, young physicists. Ever wonder why atoms don't just collapse like a spinning top losing speed? Well, Rutherford's atomic model tried to explain the atom, but it hit a few bumps on the road. You see, his model suggested that electrons orbit the nucleus like planets around the sun, but predicted a big problem. These orbiting electrons should constantly radiate energy and spiral into the nucleus, causing atoms to collapse instantly. Yet, here we are, and atoms are stable. According to classical electrodynamics, any accelerating charge, like an electron moving in a circle, should emit electromagnetic waves and lose energy, just like how a spinning ball slows down due to friction. So why don't atoms just fall apart? Also, Rutherford's model can't explain the beautiful, sharp colors we see in atomic spectra. Instead of a continuous rainbow, the light emitted by atoms appears in discrete lines, almost like a barcode. There was no mechanism in his model for these quantized spectral lines. To fix these contradictions between the classical picture and observations, the brilliant Niels Bohr stepped in. He introduced a revolutionary quantum model proposing that electrons inhabit discrete energy levels. This was our first step towards the modern quantum world, where electrons don't just spiral down, but hop between stable orbits. Let's explore how Bohr's model works. Now, let's dive into Bohr's fundamental assumptions for hydrogen, the simplest atom around. First, Bohr said electrons revolve in certain stable, circular orbits without losing or radiating energy. These special orbits are what he called stationary states. Imagine electrons on a racetrack, zooming around in fixed lanes without slowing down or crashing. Second, only those orbits where the electron's angular momentum equals an integer multiple of the reduced Planck's constant are allowed. In words, angular momentum L equals n times h bar, where h bar is Planck's constant divided by 2 pi, and n is a natural number like 1, 2, or 3. This quantization rules out any random orbits. Third, an electron emits or absorbs light only when it jumps from one allowed orbit to another, and the energy difference between orbits shows up as a photon. Mathematically, the energy difference delta E is equal to Planck's constant h multiplied by the frequency nu of the emitted or absorbed photon. Finally, the frequency nu relates directly to the energy change between initial and final orbits. H times nu equals the energy of the initial orbit minus the energy of the final orbit. Thanks to these postulates, Bohr's model elegantly explains both the stability of atoms and the discrete lines in their spectra. Pretty neat, isn't it? Let's understand this key idea, quantization of angular momentum, a bit better. Bohr assumed the electron's angular momentum, which equals mass times velocity times radius, is an integer multiple of the reduced Planck's constant. So, angular momentum L equals m times v times r equals n times h bar, where n is 1, 2, 3 and so on. This means the electron can only have certain allowed momentum values, nothing in between. Now, since the electron moves in a circle due to the positive pull of the nucleus, the centripetal force required for circular motion must balance the electrostatic attraction between the negatively charged electron and positively charged nucleus. In formula terms, mass times velocity squared divided by radius equals 1 over 4 pi epsilon naught multiplied by the square of the electron charge divided by radius squared. Here, epsilon naught is the permittivity of free space. From combining these two conditions, angular momentum quantization and force balance, we find that the radius and speed of electron orbits take discrete values. This leads to the surprising result of quantized energy levels, which explains why hydrogen's spectral lines are not continuous but come in neat, discrete packets. Imagine stair steps for orbits rather than a smooth slide. Even electrons have their comfort zones. Next, let's derive the size and speed of these special orbits. Using angular momentum quantization and the electrostatic force formula, we get the radius of the nth orbit of hydrogen atom as epsilon naught times Planck's constant squared divided by pi times electron mass times electron charge squared, all multiplied by n squared. This looks complicated, but the main takeaway is that radius r_n equals a constant a 0 times n squared, where a 0, called the Bohr radius, is about 0.5 to 9 times 10 to the minus 10 meters. In other words, the smallest orbit with n equals 1 has radius as 0, and higher orbits get bigger with n squared. Now, the velocity v_n of the electron in the nth orbit comes out as electron charge squared divided by 2 epsilon naught times Planck's constant multiplied by 1 over n. So, the speed decreases as we move to higher orbits, electrons cruising gently in outer lanes. Picture concentric circles getting wider apart, with electrons going slower the farther out they are. These quantized radii and velocities give us a fascinating glimpse into how atoms are structured, no guessing, just precise orbits. What about the energy of these electrons? The total energy of an electron in the nth orbit is the sum of its kinetic and potential energies. Kinetic energy is half mass times velocity squared. Potential energy is negative, given by minus 1 over 4 pi epsilon naught times electron charge squared over radius r_n, reflecting the attraction to the nucleus. Substituting the expressions for velocity and radius, the total energy comes out to minus 13.6 electron volts divided by n squared. The negative sign tells us something important. The electron is bound to the nucleus, kind of like a satellite trapped by Earth's gravity. The atom has less energy when the electron is tighter to the nucleus, and you must supply energy to free the electron. The minimum energy needed to ionize a hydrogen atom from its ground state, where n equals 1, is 13.6 electron volts. This number is not just a random fact. It's critical in fields like astrophysics and laser technology. So, the electron's energy is quantized and negative, confirming the atom's stability and setting the stage for spectral emissions. Now, here comes the colorful part: hydrogen's spectral lines caused by electron transitions. When an electron jumps from a higher energy orbit, say n_i, to a lower energy orbit n_f, it emits a photon with frequency nu, where Planck's constant times nu equals the difference in energies between initial and final orbits. These emitted photons form spectral lines grouped into series like Lyman in the ultraviolet, Balmer in visible light, and Paschen in infrared, each corresponding to transitions ending at different n_f values. The wavelength lambda of the emitted photon follows the Rydberg formula. 1 over lambda equals the Rydberg constant r_h multiplied by the difference between 1 over n_f squared and 1 over n_i squared. The constant r_h is about 1.097 times 10 to the 7th per meter. This formula beautifully matches the observed spectral lines of hydrogen, proving Bohr's model was onto something big. The diagram here shows vertical energy levels with arrows indicating transitions between them, giving you a visual of how electrons jump and light is emitted, like electrons sliding downstairs and shining their light as they go. Let's put this into practice with an example. Suppose an electron transitions from n equals 3 to n equals 2 in a hydrogen atom. Given the Rydberg constant is 1.097 times 10 to the 7th per meter, our aim is to find the wavelength lambda of the emitted photon. Using Bohr's formula, 1 over lambda equals r_h times the difference between 1 over n_f squared minus 1 over n_i squared. Substituting values, 1 over lambda equals 1.097 times 10 to the 7th multiplied by open bracket 1 over 4 minus 1 over 9 close bracket, which simplifies to 1.097 times 10 to the 7th times 5 over 36. Calculating this gives lambda as 656.3 nanometers. This wavelength corresponds exactly to the red line of the famous Balmer series, the bright red color often seen in hydrogen discharge lamps. Isn't it amazing how a simple quantum jump defines the colors you see? This example confirms Bohr's theory perfectly captures hydrogen's spectral behavior. To wrap up, recall that Bohr's model introduced key concepts. Angular momentum is quantized, meaning it equals n times Planck's constant divided by 2 pi. Orbit radius grows with n squared based on the Bohr radius as 0. Electron energies are negative and scale inversely with n squared, reflecting the bound nature of electrons, and the spectral lines arise from quantized jumps between these energy levels, captured by the Rydberg formula involving 1 over lambda equals r_h times the difference in reciprocals of squares of orbit numbers. These ideas not only make hydrogen understandable but paved the way for modern quantum mechanics. So the next time you see a red lamp glow or catch a glimpse of starlight, remember, it's all quantum leaps and discrete energies at play. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.